Alright, so welcome to the tutorial describing the interface for FluoroMatch, LipidMatch, PolyMatch. All of our software workflows share the same interface. And so you'll go into your software, which, for example, in this case, where you're going to use FluoroMatch 5.7. In the folder, you'll see a .bat file, and this is what's going to bring up the interface to run the software. So if you double-click that, then the interface will open. And there's a couple different aspects to this interface. These blue boxes are where you're going to drag your files on, which need to have the correct naming conventions, which we'll describe in a separate tutorial. Now, what types of files are accepted will also be described in that previous tutorial. .mzml is accepted, as well as vendor file formats such as .raw, .d, .wif, and wif2. But we do recommend, in most cases, using .mzml, but we can do the conversion in the back, and you can just simply drag vendor files here. This section down here is all of your different parameters that you'll choose that we'll walk through in depth. And then up here is your project name, where you're going to export your results, and the blank filtering parameters. On the right side is going to be all of the output of how the code's running. If any errors come up, these will show up here, as well as your loading bars. And then over here in the top right corner are links. So if you want to go to the Agilent PFAS site, Agilent's a wonderful supporter of this software that's been funding the development for the last many years. And Yale University, this is our research page, University of Florida as well. And then Innovative Omics if you need services such as trainings, algorithm support, us to run samples for you, all of that kind of thing. You can click here at innovativoomics.com. It will send you there. So if you right click, it will bring you to any of these web pages. So this is great. So now let's walk through each section. So first, let's import our data. So we need our MSMS files within this section. As you see when I drag over, it gives some tooltips, and that will actually describe the naming conventions that are needed. So in our case, we're going to have MSMS data that we're going to drag into here, acquired using data-dependent analysis and iterative exclusion. And so I've organized our data, and I like having a separate drive that has a lot of memory, then your separate different application spaces, and then the dates for each one. So let's go into a test set. We can go into this NIST data set. So this has already been exported to MZML. This is Revenant data acquired for PFAS analysis in this case. Now we're going to drag all of our MSMS, which is going to have DDMS2 in the name, into this first section, and that's it. If there's any incorrect naming conventions, so on and so forth, those will show up when you drag in. We'll also take our full scan data, and we're going to drag it in. But note, in this case, we have two polarities. You don't have to have two polarities. You can only run negative polarity. For example, PFAS gives you the most information. If you're doing lipids, we often recommend having both polarities, but you could just have a single polarity. Polymers may be only a positive mode polarity. But either way, then you're going to drag your vendor files in to the appropriate polarity section. And this is going to be all your full scan data. So I like to use shift click. So if you click one and click shift and click down, you can highlight multiple ones, or control if you want to highlight multiple samples. So you drag them in. If you need to double check, make sure you have all the samples. You can drag this to the right, make sure the names are correct, that you have all the samples you need. Note, for positive and negative polarity, if you are running both, that the samples should have the same name. So this is NIST underscore target and NIST underscore target. And then only difference is underscore pos and underscore neg. And that way it can combine the two data sets, each feature run in positive and negative mode, into a single data set. So if you had 3 samples, A, B, and C, in negative mode, you'd also call them A, B, and C in positive mode. Alright, so that's dragging your files in. There's only one other aspect I want to say here, is that you need to have a target file, so that's having T-A-R-G-E-T in the name. It's not case sensitive. And these files will be used as reference samples. So they're both going to be used to build your MS1 spectra, your EICs, and your formula prediction when you're viewing your data in the final visualizer. So you'll only see MS1 spectra, EICs, etc. for those files that have target in their name. Also, and this is just for MZMine2, they will be used to determine what peaks exist in your samples before it looks across all samples to determine the peaks. So if it doesn't exist in the targets, it won't find them in other samples. That's just for MZMine2, if you select that, which are the 2 options down here. Now, let's say you have 100 samples. In this case, we only have 1 sample, so we call it a target. Let's say you have 100 samples. Having them all as targets can slow down the peak picking process, especially for MZMine2. Also, the annotation. It can also lead to slowdowns in the visualizer as well, because you have a lot of MS1 spectras, 100 that are trying to be displayed simultaneously. Could crash the software. And so we recommend just a few reference samples. So if you only have 5 samples, you could call them all targets. Again, we're calling targets synonymous with reference samples. If you had 100 samples, I might go up to 15 targets the most. Lastly, when you're doing blank filtering, these are the ones that it's going to be used that have to be above your blank filtering threshold. Alright, so these are the samples. Note that if you have samples that don't have target in their name, they will still be peak picked and integrated. And if you have samples with target in the name, they'll also be peak picked and integrated. So you don't have to have a sample twice. If it's called target, you don't have to have a a version that doesn't have target in the name. Alright, now that we're done with that confusing name conventions, let's go into blank filtering, the one other confusing aspect of this interface. So for blank filtering, A is the percentile. So this is the percentile of your samples that have to be greater than the blank threshold, which is determined by this algorithm over here. So in this default parameters, it's 1. That means the maximum, 100 percentile, which is the maximum of your sample peak areas or peak heights. So if you had 100 samples, whichever one's highest, it will pick. So it's least conservative, has to be greater than your blank threshold. In the case of environmental samples, where every sample is unique, often I will have 1, because even if 1 sample is above your blank threshold, I want to keep it. This is from a 0 to 1, so 0.5 would be, for example, the median. This would be the median of your samples. So if you put 0.5 over here, it would say the median of all your samples has to be greater than the threshold. So for example, for lipidomics, let's say we expect all the samples to have the same lipids, just different amounts. I might put 0.5 here so that it's a little more conservative, throws a lot more garbage away. So we would put 0.5 here. So for biological samples, often I put between 0.5 and 0.8. Depends, so that it's not just if one sample all of a sudden is really high because of noise or contamination, that it keeps that sample and keeps a bunch of garbage. So it's a little more conservative, but for environmental samples, I cannot be conservative because any sample could be interesting to me, so I'm going to keep it as 1. Now, as far as the blank threshold is concerned, C, we almost always keep as 3, because this is going to be 3 times the standard deviation, which is going to cover most of what could happen by chance as far as your blank signal. So now it's average plus 3 times the standard deviation is what your blank has to be, what your sample has to be above. So if we have 1, it would just be the LOD. It would be the average plus 3 times the standard deviation. We're a little more conservative, especially for environmental analysis. I often put 2 here, so 2 times the LOD. And for biological samples where we expect very high levels, for example, of lipids, and very low background compared to the levels we'll have in our samples, I can be even more conservative, and I often put 5 times the LOD, which is also considered by some in analytical chemistry to be your limit of quantitation. So you can play with all of those parameters. Again, usually I keep C the same. A is going to depend on your study design, but you can usually keep it similar across studies. And B, I usually just keep 2 environmental and 5 for biological samples. But again, this is something I've optimized, but you can also do your own optimization. Now let's go into the other parameters that are available to us. Let's move this over. And so here are all our parameters, and you can select the vendor that your data is from. So in this case, it's Revident data, so that's Agilent, and it's after the 6546. So I'm going to click this, and all of a sudden these parameters will change. So for example, let's say I have a Thermo, one of the old Q Exactives. I will select this, and you can see the parameters change for Q Exactive versus Exploris is going to be different versus Shimatsu, Cyax, Brookers, Waters, etc. And so let's stick with the Agilent parameters. Usually these can stay the same. We'll walk one by one. So if you have MZML files that you've loaded in, like we did in this case, the first 3 parameters are not going to come into play because these are for file conversion. So these only come into play if you load the vendor file. So for Agilent, that would be .d, for Thermo .raw, for Cyax, for example, .wif, so on and so forth. So if you loaded those in, we will do conversion for you. Again, it's recommended to use MZML in many cases, and we'll walk through that in the previous tutorial, when to convert files, when to not, what to use for file naming conventions. Now, the first threshold is your intensity threshold, and again, this is for file conversion. So this is to reduce file size, which will both help limit the use of storage space, so your files will be smaller after they're converted, and it will also make the software go a little bit faster. So in the case of Agilent, we recommend 60 intensity units. So for full scan and MSMS, no data is going to be kept that's below 60. Now this scan filter in seconds has a minimum and maximum. So let's say my void volume is anything before 30 seconds is just noise. And so I don't want to keep that data, so I can set this to 30 seconds. And let's say I go up to 3 minutes, which would be 360 seconds. That can be my maximum time over here. And so you could have 30 to 360 seconds, and it will cut off all the rest of the data. Again, limiting storage space used and also speeding up the software, especially when you get to the visualization aspect of things. Not needed, but it's an option. And again, it's only in play if you're not loading already converted files in MZML format. Now, we also have a full scan peak height minimum. Now, this is used for MZMine peak picking. And so anything below 1,000 intensity is not going to be kept for our data as far as peak picking. So this is going to be the peak height at the apex. And so you'll only see features above this value. Note that there is gap filling and things of that nature. So if you do have one of your target samples, or in the case of MZ3, any sample above 1,000, then it will keep it across the rest and fill in those peaks. Noise level, so anything below this will not be considered for peak picking as 100. And then the full scan mass accuracy and PPM and Dalton are used from everything from accurate mass matching for databases to formula prediction, to alignment, to MZMine peak picking, so on and so forth. So this you want to be based on your instrument and your mass tolerance for that instrument. Again, automatically set depending on which instrument you set, but you want to make sure that your calibration is good enough to meet these criteria. MSMS intensity threshold, this one is different than the first one. This is for annotation. So if I put this at 100, While my file conversion might only keep data above 60, it has to hit 100 intensity units in MSMS fragment for it to be considered an annotation. So this helps not have false positives. Then you have your MZ search window. So that's going to be in ppm. So this will be plus or minus 5 ppm for doing MSMS matching. Now, note this is a window. So a window of 10 would be plus or minus 5. All of these other ones are tolerances. So tolerance is already plus or minus. So plus or minus 5 ppm, plus or minus 0.005. And then this one's plus or minus half. So plus or minus 5 ppm. It's a little confusing that we have both, but it is a good educational moment to realize what a tolerance and what a window is. In some software, they don't tell you whether the parameters are tolerance or windows, so you have to read or email them or guess. So at least here it's clear. And if you don't know exactly what a parameter does, you can scroll over, and for some of them, they will have tooltips that will describe that parameter. So these are the main parameters. There's also whether you're going to use peak height or peak area. There's a nice manuscript that we've published describing why to choose one over another. And so, for example, if you go to this software tool for internal standard-based normalization of lipids and effective data processing strategies on resulting values, there's a bunch of comparison of different data processing strategies, including peak height and peak area, and it goes very in depth on the differences there. But this is the main takeaway point that's easy to describe quickly, is that when we have overlapping isomers that create very strange peaks, the software is not very good at determining where the peak starts and the peak ends for integration when it's trying to calculate peak area. And so these peak areas, for example, here it took the whole peak. Here it just took this yellow peak. Over here, maybe it just took the pink one. And so from sample to sample, it's actually getting very different peak areas, not based on concentration in that sample, but based on how it's cutting off where it starts and where it finishes. Whereas peak height, as long as the isomer that's tallest is tallest more often, it will always pick that same peak height, not taller more often, taller all the time. If it has two isomers and one becomes taller than the other in a sample, then that will also cause an issue. Summary of that is that I like to go with peak height because it's more consistently picked by the software, even though peak area ideally and fundamentally would be used, but you can choose. Now, as far as our peak picking algorithm, right now we have two options, MZMine 3, MZMine 2. We've chosen MZMine because we've done benchmarking studies across MZMine, XDMS, and MS-Dial, and at the time, so things may have changed, MZMine did perform better in our view based on our metrics for the data sets that we used. And so we chose MZMine to incorporate into our software, and they've been very gracious to allow us to incorporate their peak picking algorithms into our open source software, so please cite them if you use it. Now, MZMine 2 is slower and does crash, needs a lot of RAM, it loads everything up into RAM at one time, but it gives you better peak picking in terms of making sure it gets all the peaks usually that are high quality are picked by MZMine 2, and that it gets less noise and considers those peaks. Whereas MZMine 3 is way faster, does not crash very often, it's very quick, even for large sample studies. So if you're doing large sample studies, definitely have to click MZMine 3 depending on your computer. But it does sometimes miss peaks and sometimes get more noisy background as far as the peaks are concerned. So I often go with MZMine 3 because I'm impatient and I want things to run fast, although MZMine 2 does give you better quality in most cases. But they're both good. Now, as far as we go, that is the main parameters that you'll choose from. And so now we can just choose our project name. Just keep this name short because it's added to all the files, and if the file names are too long, sometimes Windows gets upset. So I'll just call this nest. and then a directory for exporting the results. So once you have created your folders in the output, then you can click Start. And once you click Start, then you will see all of the different outputs from the code in your right panels. If there's any errors, these will also be saved into a folder that you can send to me. There'll be a separate troubleshooting tutorial. And so all of these will be run over here. And then I do want to just go over some of these parameters. So all these are optional. The all ions one are if you have all ions files in your data set. Again, as we discussed when we talk about data acquisition file types, we don't recommend all ions as your only way of acquiring MSMS because it's really hard to tell where those fragments came from because there's no ion selection. But let's say you do have all ions data as a supplement to your data dependent or iterative exclusion, or you're working with someone or yourself who has old data that's just all ions, that is fine, and you can use it. And we do deconvolution. And so you would put the number of scans that you need for a fragment to be considered real and for it to correlate to precursor ions and your correlation cutoff. If you want to understand more about how these parameters work, please go to this publication, Expanding Per and Polyfluorosubstances Coverage and Non-Target Analysis Using Data-Dependent Analysis and Ion Decon. And we'll put a link to that in the comments as well. Now there's also this targeted peak detection. So this is just if you use MZMine2. And this is in the case, let's say, where you have a number of peaks, such as your chemical standards, that you want to make sure are picked when you're doing your analysis. And so you'll have this targeted peak list, and it will both do the non-targeted peak detection, as well as make sure it includes those that you give a certain retention time and mass to charge for. So if we go into our templates folder, so if you're in your FluoroMatch, LipidMatch, or PolyMatch folder, and you go into the templates folder, here you'll see this targeted _neg table. And if you double click that, then you will get your MZRT row ID formatted table. Just replace the MZs, the RTs, with what you need. Row ID just put some kind of number. It doesn't actually keep this naming as it picks peaks in the final table. So you'll have to relook at what was your standards or so on and so forth. So that's how you would do targeted peak detection. For statistics, you put a grouping file. Also in this template folder, you can see groupings. All the groupings file is the names that have to be, or the character string that needs to be in your file names. So all files that are in this case controls have to have CNRTL in their name. And all files that are, let's say in this case, liver samples, have to have LIV in their name. And so, or with the underscores in this case as well. And so make sure that all of your controls, treated, wild type, you can have any naming conventions. You just have to keep that name in all of the files. And I mean by all the files, it would be all of these files, either in your negative, positive, or both, if you run both polarities. In this case, we only have one file in this C, and so you wouldn't want to have the groupings in the names of all the files here. And that will give you statistics. Currently, statistics are beta, so if you do have errors, which you may expect running into statistics, then feel free to reach out. So that's it for this tutorial. Our next tutorial is going to cover what you do when you get all your outputs, how to read the tables, and then following which we'll have a tutorial on using the visualizer and uploading the files into the visualizer. So with that, I'd like to thank you, and feel free to reach out. Reach us at innovative omics.com. Again, you can just click this little green dot over here and find our contact and contact us there if you have any questions, or feel free to leave comments in the YouTube video.